Hello everyone. I'm Samatha Ereshi Akkamahadevi. I'm a master student at the Department of Computer Science, Kansas State University. Today I'll be presenting a demo of our automation pipeline, which is designed for CNN neuron interpretation. Previously, Abhilekha Dalal has worked on interpreting the CNN hidden neuron activations through concept induction and semantic reasoning methods. Here, the process was mostly dependent on manual intervention at every stage. Like during the model training, the outputs were manually analyzed to prepare the inputs for the subsequent stage. Also, the tasks were sequentially executed for each neuron. And the results were consolidated and validated manually, and the statistical test for each neuron was performed manually. Additionally, the code for each stage were executed on different software platforms. So it was time consuming, often taking several days to complete the entire process. To address these challenges, I have automated the entire process by eliminating the need for manual intervention at all the stages. This automation significantly reduced the execution time, improved the performance, and minimized the potential for human error. Additionally, our pipeline is easily adaptable for different data sets and different training conditions, which will enhance its applicability and effectiveness. Basically, our pipeline consists of 4 main stages. In stage 1, we perform model training and data configuration. In stage 2, we perform parallelized concept induction and label hypothesis generation. In stage 3, we validate the label hypothesis generated in stage 2 using parallelized image retrieval and classification methods. In stage 4, we perform statistical analysis and verify the neuron activations. We wrote bash scripts for each of these stages, like bash script for stage 1, stage 2, stage 3, and stage 4. And we executed these bash script on BioCat, which is a high-performance computing environment offered by Kansas State University. This approach automated the job scheduling, resource allocation, parallel processing of tasks, and reduced the overall execution time of the entire pipeline. With this background, now I'll proceed with the demo to discuss each stage of our pipeline in detail. Beginning with stage 1, basically this stage involves data preparation, model training, and saving the trained model for further analysis. Let's take a look at the bash script for stage 1 now. This script will help us in automating the job scheduling and in resource allocation. Here I have specified the resource required for executing this script using the sbatch command. Also, this helps us in setting up the required Python environment, which is Python 3.11.5, and it has securely cloned the stage 1 code from GitHub repository. Then it installs the required libraries or dependencies, mainly TensorFlow, SciPy, Pandas, etc. And then it has a command to execute the stage 1 code. To run the stage 1 code, we can execute this particular bash script in BioCat shell access by entering the command sbatch. This is the command sbatch, and we have specified the bash script file name for stage 1. After executing this command in BioCat, we get the job ID and corresponding log file. So this is the job ID of previously submitted batch, and this is the log file for it. Also, it has generated the outputs of stage 1 in the specific output directory. We have trained the CNN model based on ResNet 50 V2 architecture with Adam optimizer and categorical cross-entropy loss function. The model is trained using 6,187 images that belongs to scene classification image that have 10 different classes from the ADE20K dataset. Also, early stopping was implemented to prevent the overfitting of the model. And we have trained our model like this. After training the model, we have saved the trained model in .h5 format in the output directory. So this is the .h5 file. So this step is made to ensure that the trained model can be loaded and it can be used for analysis in the further steps without retraining it again. Now we'll reload the save model for analysis, and the outputs of the dense layer are extracted to create the feature map model. This will be used to understand the activations of hidden neurons in this layer. We choose to look at the dense layer because the previous studies have shown that the earlier layers of CNN respond to low-level features such as lines, stripes, textures, colors, while the layers near the final layer respond to high-level features such as face, box, road, etc. The high-level features align better with the nature of background knowledge we have used, that is derived from the Wikipedia concept hierarchy. Next, we evaluate the performance of the model using classification report. This is generated using the test data and predicted labels. Here, the evaluation metrics include precision, recall, and F1 score, which provide us the insight into model's accuracy. Then the feature map model is used to make the predictions on the test data set, and it generates a CSV file with the prediction results. These predictions will have the class probabilities and corresponding file names. Also, the model focuses on activations of specific neurons in the dense layer to understand how the model processes images. Generally, the dense layer consists of 64 neurons. We choose to analyze each of the neurons separately. Let's take a look at the output. Here is the CSV file, which contains predictions of 64 neurons from the dense layer. Let me open it and show you. So these are the class probabilities for all the neurons starting from 0th neuron to 63rd neuron, and corresponding file names have been mentioned over here. Next, these neuron activations are analyzed to generate the positive and negative image sets. So the positive image sets are those which contains list of images that strongly activate a particular neuron, that is above 80% of maximum activation, while the negative image set are those with a list of images that does not activate the neuron strongly, and they have the values below 20% of maximum activation. And here you can see few random neurons does not have any activations from the source images. So such neurons will be skipped while doing the further analysis. Finally, we generate the configuration files for each neuron, and those configuration files are fed to the next stage to perform the concept induction analysis. These are the configuration files generated. So let me show you one example of neuron 41, which contains positive image set, negative image set, and also we have specified the path to background knowledge, which is in the form of .all file. Now let's take a look at the execution results of stage 1. Here we can see that the stage 1 job has taken around 38 minutes, 50 seconds, completing under 40 minutes. And if we want to take a look at the resource used by this job, it has basically used 24 CPUs across 4 nodes, utilizing 4.87 GB of memory, and has completed under 40 minutes. Now let's move on to stage 2 to see the parallelized concept induction and label hypothesis generation. In this stage, we use EC tool, Efficient Concept Induction Implementation Tool, which is developed in Java by Mohammad Sarkar to generate the label hypothesis based on the concept induction process. EC tool uses a large-scale background knowledge base to assign the meaningful and human understandable labels to neuron activations. This will help in enhancing the transparency and interpretability of the neural network model. Now let's take a look at the stage 2 bash script. Here we have specified the resource allocation using the dispatch command, and it helped in initializing the required environments such as Java 1.8 and Maven 3.6.3. Then it securely clones the stage 2 code from the GitHub. Followed by that, it installs the necessary dependencies to execute the Java program. Mainly, it contains the command to execute the Java program for each of the configuration files generated in stage 1. And over here, we have implemented the parallel processing to run the Java program concurrently for all 64 neurons. That helps in drastically reducing the overall execution time. To execute this bash script, we used sbatch command to place the job, and it generated a unique job ID with log files and the outputs in the specified output directory. So each neuron specific configuration file from the stage 1 was processed by EC tools separately but simultaneously to generate the semantic concepts for each neuron. And output of this process is a set of text files. So these are the output text files generated by EC tools for each neuron. These contain the hypothesized labels. As we can see here, this is the output, and here is the list of solution, which is human understandable, and they are in the form of keywords. And these solutions are sorted based on the coverage score currently. By making few changes to automation, we can change the criteria and we can sort the solution based on the F1 score. Now let's take a look at the execution results of stage 2 bash script. Here we can observe that it has created 64 subjobs under the main job. And each of these subjobs correspond to a specific neuron. They take about 10 minutes to execute. The overall job started around 15:06, and then it was completed around 15:23, taking about 17 minutes to complete the entire stage 2 code. This optimization not only demonstrates the robustness of our pipeline, but also it showcases the practical applicability of advanced parallel processing techniques in improving the model interpretability. Here we can see that the job efficiently utilized the allocated resource, completing under 20 minutes. Each of the sub-job used a single CPU with single node and 20 GB of physical memory each. So we can say that parallel execution accelerated the processing time compared to sequential execution, which would have taken approximately 10 hours to process each neuron individually. In the third stage, we automate the process of image retrieval and classification to validate the label hypotheses that were generated in stage 2. This involves two main bash scripts. The first script takes few seconds to generate the indices for neurons with configuration files and text files that were created in earlier stages. Then the second script uses these indices for parallel task execution. Now let's take a look at the bash script of stage 3. In this script, we have specified the resource requirements to execute this particular script and set up the Python environment, Python 3.11.5. After securely cloning the GitHub repository for stage 3 code, it actually installs the required libraries such as Python Magic Bin, PyGoogle Image, TensorFlow, and Pandas, etc. It also contains the command to execute the stage 3 code. Here also we have implemented parallel processing to execute the tasks in parallel for all 64 neurons. Next, we extract the top 3 keywords from the outputs of EC file. For each keyword, we retrieve 100 images from the internet using PyGoogle image library. Then we organize them into appropriate directory. As you can see here, we have retrieved 100 images for top 3 solutions for all the neurons, and they have been arranged in these directories. Suppose for neuron 9, we can see that it has got 3 solutions, and in each solution, there is a keyword for which 100 images have been downloaded. Next, we classify these images using the already trained CNN model from stage 1. And then these images are split into evaluation and verification set, and the results are saved in the CSV files for top 3 solutions of each neuron. Here you can see that evaluation and verification folders have been generated as output of stage 3. If we take a look at these, we can see that evaluation sets have been generated for top 3 solutions for all of the neurons. Likewise, in the verification folder, verification sets have been generated for top 3 solutions for all the neurons. These CSV files are important for statistical analysis that will be performed in stage 4. Now let's take a look at execution results of stage 3 bash script. Here we can observe that 64 subjobs have been created under the main job. On an average, each of these subjobs are taking around 6 or 7 minutes to execute. Overall, the process began at 1622 and finished by 1631, taking about 9 minutes. This job efficiently utilized the allocated resources, completing under 10 minutes. Each subjob used the single CPU on single node and utilized approximately 1 GB of memory. Again, this parallel execution accelerated the processing time compared to sequential execution, which approximately takes 10 hours. Additionally, this automation eliminated the manual intervention, ensuring consistent and reproducible results. The final stage involves rigorous statistical analysis and verification of neuron activations that were generated in stage 3 to validate the label hypothesis produced from concept induction in stage 2. So now let's take a look at the stage 4 bash script. So this bash script is helpful in allocating the resources and setting up the Python environment. Also, it clones the stage 4 code from the GitHub repository and installs the necessary libraries such as pandas, OpenPyXL, and SciPy, etc. Finally, it runs the stage 4 code. We have two main phases in stage 4, evaluation phase and verification phase. The evaluation phase, we analyze the activations of neuron using the data generated from stage 3, which are stored in evaluation and verification folder. To do that, we combine the activation data of each neuron and solution type into a single data frame and consolidate it in the evaluation combined Excel workbook. This allows us to perform a comprehensive analysis of neuron activations. Then we generate key activation metrics such as target activation and non-target activation to understand the activation patterns of the neurons and corresponding label hypothesis. Then we apply the formatting to highlight the neurons with significant activations. This ensures the data is easy to interpret and the highlighted data will be moved to final summary sheet. In the verification phase, we validate the neuron activations using statistical tests to ensure the robustness of label hypothesis. We start by reading the final summary data from the evaluation phase to identify the neurons with significant activations. Then we process the verification data for each neuron present in the final summary of evaluation phase and combine it into a single data frame for analysis. And this will be saved in verification combined.excel workbook. Next, we conduct Man-Whitney U-test to get the z-score and p-value to compare the activation values of target and non-target images. This helps us to determine the statistical significance of neuron activation. Here we highlight the rows which are statistically significant based on the p-value, which will be less than 0.05. This thorough statistical analysis helps us in validating and confirming the accuracy and robustness of label hypothesis that was generated in stage 2. Now let's take a look at the execution results of stage 4. As we can see here, stage 4 job has efficiently utilized the allocated resources, completing under just 3 minutes. It has used the single CPU on single node, utilizing 0.8 GB of memory. In conclusion, I can say that our automated pipeline for CNN neuron interpretation using concept induction significantly enhanced the explainability and performance of deep learning models. By automating and parallelizing the stages for model training, concept induction, image retrieval, and statistical analysis, we have drastically reduced the execution time and minimized the manual intervention. Thank you for watching this demo. If you have any questions or need further details, please feel free to reach out to me at samatha94@ksu.edu.